Hello guys, welcome back to Introduction to Number Theory. This time we will discuss some examples of Diophantine equations where we need to use combination of methods, different methods, in order to solve the equation and maybe gain some interesting results. Let us consider such a notion like perfect numbers. What is a perfect number? Well, we say that n, a positive integer, is perfect if it is equal to the sum of all its proper divisors. Where by proper divisors, I remind you that we understand divisors of n which are less than n. So 1 and some other natural numbers will be proper divisors, but not n itself. In other way, we can write this as an equation where 2n, 2 times n, is equal to sum of all of divisors of n. What can we say about perfect numbers? Do they exist, such numbers? Well, let's consider several examples of perfect numbers. Say number 6. It's perfect because 6 has divisors 1, 2, and 3. Besides itself. And 6 is equal to 1 plus 2 plus 3. So it is perfect according to our definition. Another perfect number, also very famous, is 28. Well, let's check if it's perfect. 28 is divisible by 1, 2, 4, 7, and 14. And it is easy to check that 28 is exactly equal to sum of these divisors. So we need to ask ourselves, what is general form of perfect numbers? Is there a formula which would give us perfect numbers in an infinite amount? Well, actually such a formula exists, and we have a theorem which states that if n is even perfect number, then and only then, n has form, which you see here on the slide, which is rather complicated, but soon we will get used to it. So let me explain. We have two factors. First factor is the power of 2, and the second factor is a prime number, which actually has a specific form. So this theorem states that all even perfect numbers are given by this formula. Well, you might ask, what about odd perfect numbers? This is an interesting question because we don't know whether odd perfect numbers exist or not. Let us now prove this theorem. Well, since theorem is like an equivalence, we understand that we need to prove it in two directions. First, we will prove it from the right-hand side to the left-hand side. Let us consider n given by this complicated, so to call it, formula, and calculate the sum of all its divisors. Well, we know that sum of divisors is a multiplicative function, so first we take the sum of all divisors of the power of 2, and we understand that these numbers are also powers of 2. And then we take all divisors of the second factor, which we know is prime, so all its factors are just number 1 and this number itself. Then we simplify this expression and clearly see that is really equal to 2n. So this proves that all numbers given by the formula in the theorem are perfect. Now we need to prove this theorem from the left-hand side to the right-hand side. And for that purpose, let us transform number n into a product of the power of 2 and some odd number. We understand that every natural number can be represented in this form. And let us calculate, or just write an expression, for the sum of all divisors of n. Well, we understand that sum of divisors is a multiplicative function, so we take separately sum of all divisors of the power of 2 and sum of all divisors of n. We don't know anything about m yet, except for its odd. So we understand that sum of all divisors of the power of 2 is given by this fraction, and some unknown factor which is equal to sum of all divisors of m. Well, let us take a very patient look at this expression. We understand that it is sum of all divisors of n, and we understand that it needs to be equal to 2 times n. So this is an equation we need to solve now. Now we understand that m is divisible by 2 to the power of alpha plus 1 minus 1. Why is this so? Well, on the right-hand side, we see two factors. The first one is the power of 2. Second one is m. And on the left-hand side, we see this expression, 2 to the power of alpha plus 1 minus 1, which is obviously odd. And we understand that power of 2 and an odd number are mutually prime. So m must be divisible by this odd number. Let's denote by t the result of division of m with this odd number, and go on with the proof. Let's rewrite this equation in the following way. First, write the fraction formed by the sum of all divisors of m and m itself. We understand that it needs to be equal to the fraction formed by parts of the equation that contain powers of 2. Then we can a bit transform obtained equation. First of all, we can write that the fraction is equal to 1 plus another fraction. And also we can rewrite fraction that has m in the denominator and sigma of m in numerator. We know that 1 is a divisor of m, we know that m is a divisor of m, and maybe m has some other divisors. And then, using the result from the previous slide, we can rewrite this as 1 plus t over m plus some other summand. What is t over m? Well, t is one of the divisors of m. And we clearly understand that t is not equal to m. So let us compare two sides of the obtained equation. Now we see 1 and 1, so we understand that they are equal. And we see this fraction and this fraction, and we also understand that they are equal. But what about all the other summands over here? There must be no other summands, otherwise this equality would be false. So we understand that this set of summands is empty. And from this, it follows that the sum of all divisors of m is equal to m plus t and nothing else. And from this it follows that t must be equal to 1 and m must be prime. So also we gain that m must be equal to the power of alpha plus 1 minus 1. This was a famous result obtained by a very famous mathematician called Leonhard Euler, who did very much for the number theory.